models.
Thanks, Lisa. It's my great honor to be here to present our recent work with Peter. And my first encounter with Peter was at Beijing. Back then, I was still an undergrad in Peking University, and I was working on some econometrics problems that had something to do with non-parametrics, and we'll use some techniques like strong embeddings. So I got a chance to read some of Peter's very old papers in the 60s and 70s. I don't know if you still remember that. But then one day I received a talk announcement saying Peter Bickel will come to Peking University to give a talk. And I was so shocked. And I just went to the talk. And turns out it's not just one talk in Peking University, and there are also 2 other talks in Tsinghua University. So I attended all of them. So I just follow him. And it was so nice that Peter even set up 1 hour to chat with me and brought up some very important references, turns out to be crucial in my undergrad thesis. And so then I began to wonder, that's before my PhD application. So I wonder if I were to get a chance to go to Berkeley to do my PhD, I would definitely ask Peter to be my advisor, if that's possible. So the first day I came to Berkeley, came to the Evans Hall, I just stopped by Peter's office. And I wasn't that straightforward, but basically I was saying, can you be my advisor? And Peter said yes. So then the journey started. And I'm sure that, as with all other Peter students, it's so enjoyable to work with Peter on projects and making progress and solve hard problems. But here, today, I'm not going to highlight that part. What I want to say is, it's also very exciting when I got stuck in a project. Because there, you can just come to Peter's office and say, let's derail this conversation. Let's think about something else, which could be crazy. And here, say, Peter, I got this crazy idea, which I found there is at most 5% of chance to work out. And instead of saying, don't waste your time on that, Peter would say, tell me about that. And very often, almost every time, Peter will give me some positive feedback. And eventually, I think my estimate of 5% is quite accurate. It's very calibrated in the sense that maybe only 1 out of 20 crazy ideas eventually work out. And here's one of them. So this is a very unusual work, where we propose some methods. But at this moment, at least now, I didn't expect any of you to use that. So I'm not going to give you a cell of this method. But in the meantime, I think I can walk through every detail in the paper, nearly every detail in the paper in 30 minutes. So you will see how weird it is. And this is perhaps one of the weirdest ideas I've ever had with Peter. And as with other speakers, I also look at the mass genealogy, and I found myself the 61st students of Peter. So I'm definitely among the youngest students of Peter. But today I'm going to talk about one of the oldest problems in statistics. That is how to do hypothesis testing for linear models. And our setting is so simple. Here you have a linear model, you have y, and you have an intercept, and you have a covariant matrix X, and some unknown coefficient beta star, and some random error. And now the goal is to test whether some linear contrast of beta star equals to 0. And in particular, without loss of generality, you can do some rotation, because this is for fixed design matrix. So you can do some rotation to change that hypothesis into something called a sub-hypothesis, which is to test whether the first R entries equal to 0. So maybe the most interesting case would just be to test whether the first entry equals to 0 or not. And this is, of course, one of the most ancient problems. And it starts from this guy. So anyone has a guess of who this is? Yes. This is William Gossett, also known as Student. So in 1908, he wrote 2 papers, which basically established the foundation of the t-test. The first one is on one sample t-test. And the second one is on two sample t-test. So turns out that's a special case of the linear model, where the first one can be viewed as testing whether the intercept equal to 0 with no nuisance parameters. And the second one is a one-dimensional linear model, and you are going to test whether that coefficient, the slope, equals to 0, with the intercept being the nuisance parameter. And later on, Fisher got really excited about this idea, although Students' work didn't pick up much attention back then. I think it was pretty fortunate. Only Fisher noticed that work, and then he pushed that forward. So in 1922 and 1925, he completely generalized these ideas. So like in the 22 paper, he talked about how to test the global now while treating the intercept as a nuisance parameter. And then in his elaborated monograph, Statistical Method for Rich Workers in 1925, he generalized that. And so now we are going to talk about this problem. And because this is a century-long problem, whatever we're going to propose, we need to ask ourselves this question: is that really new? Because it's been 100 years. Whatever method you are proposing, there might be something happening in 1960s or 70s or 80s, and there might be a paper there which has been forgotten in history. And you can't claim that your method is new. So for that reason, we actually did a literature review from 1908 to 2018. And we call it a selective review of the century-long effort. And this is Appendix B of our paper. And this review includes about 250 references, but I don't think it's exhaustive. So I'm definitely missing a lot of important ones. But the reason I call it selective is that in this review, we only focus on the most generic problem. So there's no high dimensions, there's no sparsity, there's no Bayesian things, there's no breakdown points. Just on this pure problem, we reviewed like 250 papers. And roughly speaking, we can categorize the existing tasks into those classes, where then regression RML estimate-based tasks, and actually Peter is the pioneer of the L estimate test, and then bootstrap tasks, and some non-standard tasks. And I think what's fascinating about this is that now I got a chance to look at the history and to see what happens. And there are some surprising things. So for example, I thought the rank test was way later, but it can actually date back to Milton Friedman in 1937. And also for symmetry-based tests, there has been some works by Henry Thiel, the inventor of two-stage least squares and many other things, in 1950. So you can see, you can really date back to very early history of statistics to get some of those. And many of these methods are working very well. They're shown to be very robust in many settings. So that's why we're not going to propose a superior method that dominate this method, but we're going to ask this question: when are these tests exact or valid in finite samples? So suppose I'm someone who don't like asymptotics. We just have this finite sample, and we want our type 1 error to be exactly controlled. Then what conditions do they need? Turns out this is a little bit frustrating. So what we can, in our review, we found that, for example, the T and F tests are exact with Gaussian errors. And I talked with Steve Stigler on this, and he pointed out that actually Fisher never required Gaussianity because all of his proofs are purely geometric. So the underlying assumption should be rotation invariance. But an old result from Maxwell in 1860 shows that if you have rotation invariance and independence, then it must be Gaussian. So that means rotation invariance is a strong assumption. And the permutation tests are very robust, but in theory, they're only exact for global now or certain ANOVA problems. And rank-based tests and also the test based on regression RML estimate can also be made exact for global now. And there are some non-standard tests like Hartigan's typical values, which I found really interesting, but I don't think many people know about this. And that can be made exact for some balanced ANOVA problem with symmetric errors. And finally, there's a recent work by Michelson in 2015, which is exact for rotational invariant errors with no noise level. So you can see all these assumptions are very strong. Another question is, can we derive the exact test for sub-hypotheses? So there's a very simple strategy, which is you can look at the global now, and you can use any exact test and invert it. So that will give you a joint confidence region for every parameter, including all the nuisance parameter. And then you look at projection. But that's going to be very conservative because you are not focusing your power on the parameter of interest. And often it's computationally infeasible, even with the moderate p, like 10. But the question is, why are these exact tests for sub-hypotheses so hard to come by? I think there are two of them. One is most exact, or one of them. Most exact tests are exploiting some group invariants, like permutation test or randomization inference. But often they assume that there's no nuisance parameter, or under the null, you have a simple null after conditioning on this randomization. But when you have nuisance parameter like the other coefficient, it's very hard to maintain the group invariance. But on the other hand, why are exact tests so important? I think first, many tests would essentially require that you can consistently estimate all the nuisance parameters. But that's hard. Like for me, one big thing in my research agenda is how can you get valid tests without consistently estimate the entire system? So we want that. And the second thing is it's simply an intellectual challenge because no test is exact under reasonably general assumptions over the past 110 years. So in this talk, we will introduce a test called Cyclic Permutation Test, which is valid in finite samples for arbitrary fixed design matrix X and arbitrary exchangeable errors epsilon. So you don't need moments, you don't need assumptions on X. And of course, if X is too bad, then you wouldn't have power. But this will achieve exact type of error if 1 over alpha is an integer. And further, it will be non-randomized if the ratio between the sample size and number of nuisance parameters is greater than 1 over alpha. And moreover, through simulations, we can show that it will achieve a reasonable power if this ratio is much larger than 1 over alpha, like 1.5 over alpha. So for example, if you want to test whether the first entry equals to 0 with alpha equal to 0.05, you just need n over p to be bigger than 20 for validity and 30 for reasonable power. So what's the idea? So the idea is that let's construct a pool of statistics which are linear combinations of y. So here, y is an n-dimensional vector. And we're gonna construct some linear combinations. And our goal is to say, if this set of statistics has some properties, which I will introduce in the next slide, we will calculate the rank of the first one. And we hope that this rank is uniform under the null, but extreme under the alternative. Then we will reject each null if this rank is extreme. So in particular, of course, we would think about exchangeability, but in order for this test to work, we don't need exchangeability. We just need a cyclic permutation group. So here we will call this set of statistics invariant under cyclic permutation group if the distribution doesn't change if you move the elements, one element to the right. So in other words, this group only has m plus 1 element. It doesn't have m plus 1 factorial elements. Then this is almost a trivial result that once you have this property, then if you do any transformation of the scores and you calculate the rank of the first one, then that rank would be uniform if there's no tie. And as a result, if you normalize that rank by m plus 1, it will be a valid p-value. And moreover, if alpha equal to some multiples of 1 over m plus 1, then this will be exact. Okay. Now the question is how to construct these coefficient factors. So recall that we have two goals. One is we want validity, meaning that this set of statistics should be invariant under this group, under the null. But in the meantime, we want high power, meaning that under the alternative, the first one will be larger. So let's talk about validity first. So first, we've partitioned X into two parts, one corresponding to the first R columns, the other corresponding to the rest. And then Y can be written in that way. And then any linear combination of Y can be written in the following. So there are three terms. And then under the null, the first term goes away. So we are left with two terms. The first term is deterministic, and the second term is random. So the idea is quite simple, is that what if we can match the deterministic part and make the stochastic part invariant under the cyclic permutation group? If we can achieve that, then we're done. Okay, so let's look at how to achieve that. So the first one is, the simplest way to match the deterministic part is to make that coefficient, the eta transpose X minus R, to be the same for every linear combination. So let's call this common value gamma minus R. So the first set of conditions for this ATAs is that they should satisfy the first bullet point. Okay, that's a set of linear equations. And then we need to think about how to make the stochastic part invariant. That's perhaps the most important part in this talk. So it turns out the intuition is quite simple. If all these vectors are shifted version of the other, then this set of linear combinations should also be invariant under the cyclic permutation group. And for simplicity, let me give you an example with 6 samples and m equals to 2, so that we are going to construct 3 statistics. And in this case, 6 divided by 3 equals 2. So we will let eta 0 to be eta 1 star to eta 6 star. And then we will let eta 1 to be eta 3, 4, 5, 6, 1, 2. And eta 2 to be 5, 6, 1, 2, 3, 4. So every time you just move 2 elements to the left. If this holds, then we show that the stochastic part will be invariant. Let me explain why this is true. So this is a special case where let's rewrite these 3 statistics. So we know that this 3 statistics would be equal to this matrix of etas multiplied by the error term. And of course, we can exchange eta and epsilon. So we get a matrix of epsilon multiplied by a vector of eta. And then if we shift one statistic to the left, we will get the same thing. So again, we will get a matrix of epsilon multiplied by a vector of eta. And then if epsilon is exchangeable, these 2 matrices of epsilon will have the same distribution because they're shifting the rows. And as a consequence, these 2 random vectors would have the same distribution. So you can apply the same logic to get this invariance. And then you may ask, is this cyclic permutation group an artifact, or do we actually have the exchangeability? So if we have that, then we don't need to talk about this. But actually, we don't. So let's look at another permutation of the 3 statistics, where you just exchange the last 2. So this is not a cyclic permutation. Then you can rewrite this as a matrix of epsilon multiplied by eta. And you can find these 3 elements. So you see, in the left, those 3 elements are equal almost surely. But in the right, they're not. So in general, without further assumptions, these 2 vectors do not have the same distribution. So in other words, under this construction, they're only invariant with respect to the cyclic permutation group instead of the exchangeable group. So now let's get back to this. So in order to match the deterministic part, we have this set of linear equations. And in order to make the stochastic part invariant, we need eta j to be shifted version of one vector. And turns out the second one is also a linear equation. Because you can imagine that this left shifting operator is a linear operator. So you can just define this capital pi as the permutation matrix corresponding to that left shifting. And you can rewrite the set of conditions as a linear system. Okay. So the whole thing, in order to get a valid test, you just need to solve a linear system. Now let's get back to our linear algebra 101. When does a linear system has a solution? We know that that would happen as long as the number of variables is bigger than the number of equations. Now let's do the counting. So here, the number of variables is the dimension of gamma minus r and eta star. So gamma minus r is p minus r, the number of nuisance parameters, and the dimension of eta star is n. So overall, you have n plus p minus r variables. The number of equations is just the total number of rows of this matrix. That's going to be n plus 1 times p minus r. So as a result, we only need n to be bigger than p minus r times m to get a valid test. Here is just a summary. Again, I think once you figure it out, everything here, there's no technical argument. It's just linear algebra 101. So assume n is divisible by n plus 1, then this linear system will always have a non-zero solution as long as you have this ratio bigger than m. And for any solution, this will give you a valid test. That's the first part. And some general comments. First, we want alpha to be a multiple of 1 over n plus 1 in order to get a non-randomized exact test. Because here, the p-value only take values as multiples of 1 over n plus 1. So in particular, if 1 over alpha is an integer, we can simply set m to be 1 over alpha minus 1. In the case where alpha equal to 0.05, you can just set m to be 19. So in this case, we just need the ratio of n and number of nuisance parameters to be at least 19. So this is quite reasonable assumption, at least in social science. And also when R is large, like say you have a lot of fixed effect, which are nuisance parameters, but we want to test global now, then you can do better. Okay, that's about validity. But valid test is not hard to come by. You can do some arbitrary things by generate a random number, random uniform random variable. But here we also need to talk about power. And for power, let's assume we're just going to test one coefficient, like beta 1 star equals to 0. Then we will have 3 parts. And under the previous construction, we have already shown that the second 2 parts are invariant. So all the signal part will go to the first component, which has something to do with beta 1 star. And to enhance power, we simply want the coefficient in front of beta 1 star to be much larger for the first statistics. And a very simple setting to make that happen is to set all the others to be equal and set the first one to be that number plus some delta. And here, if all these eta j's, the coefficient vectors have norm 1, you can view this delta as a signal to noise ratio. So let's put them together. And you can see here, in order to get a good power, we just add a bunch of new linear equations. And again, we can rewrite them as a linear system. And we can apply the same reasoning. So as long as the number of variables is larger than the number of equations, we will have a solution. And in this case, the condition would be n over p bigger than or equal to 19, or m. And then here, because when we have that condition, a linear system has infinite solutions. And because X is deterministic, so we are free to choose any one we like. And the very natural idea is to find the eta star vector such that the signal to noise ratio is maximized. So let's solve this linear programming problem where our objective is just to maximize delta. And our constraint is that giant linear system. It turns out this is very easy to do. It just has something to do with OLALAS. You just run OLALAS of one column in that coefficient matrix on the others, and that will give the answer. So I wouldn't delve into detail. The point of this result is just to show that it's very easy to get this number. So far, we have using some weird techniques to get this test. But now here comes the weirdest part. So let's review this coefficient matrix. You see that here we have this X transpose pi. And the pi is corresponding to the left shifting operator. So in other words, it will, let's say m equal to 19. So it will divide X into 20 chunks. And every time it will move the chunks to the left. That means this test depends on how you arrange the rows or the observations of X. Right? This doesn't hold for any other test, because any other test, if you do t-test or f-test or permutation test, it wouldn't depend on how you rearrange the rows, but this one does. So as a result, this delta star, the signal to noise ratio, as a function of the permutation of the rows of X, it does depend on that permutation. And here's a quick simulation to tell you how much fluctuation you have. So here I generate 3 matrices, one from Cauchy, one from normal, one from T5, and I just generate one copy of that. And then I generate a lot of permutations of the rows, and each time I calculate this delta star. And here's the histogram. So you can see for the Cauchy case, the largest one has signal to noise ratio 6, but the smallest one has that only a half. So that means if you can find a good pre-ordering of the rows, you can have 12 times larger signal to noise ratio. So that means we have to do something here. So here, the ideal thing is, let's just maximize this signal to noise ratio with respect to all the permutations. And we know that this is a nonlinear traveling salesman problem. It's definitely NP hard. There's no solution. Anyone who had come up with an exact solution would win every award in the world. But here, fortunately, we don't need to exactly solve this. We just need a good value, or we just need a good permutation. So in our work, we just apply the genetic algorithm to find a good permutation. And we implemented that by some R package. And here's the illustration. So I simply compare this genetic algorithm with the naive stochastic search. By that, I mean, you just randomly choose some permutations and then take the best. So you can see that, like here in the x-axis, we give the number of samples. And in the y-axis, I give that delta star x. Sorry, that's a typo. And you can see genetic algorithm can actually improve over time, but stochastic search will quickly get trapped in a local minimum. That's not surprising because this is a giant space. It's very hard for a random search to get to the right point. So just to summarize this test, and that's already the test. So first, we apply the genetic algorithm to find this ordering, and then we reorder y and x, reorder the observations. And let's call that y tilde x tilde. Then we use our method to compute that eta star by solving that giant linear system. And we compute this score, which is the linear combination of this y tilde. And in the previous slides, I only talk about one-sided test. So you can directly calculate the rank of the first one, but also works for two-sided test because you can do any transformation of those scores as long as it's exchangeable. So for example, you can subtract the median of the scores from the first one and then calculate the rank. And finally, you calculate the p-value. And if you don't want randomization, you can simply use R over n plus 1. And finally, you reject the null if the p-value is below alpha. So that's the test. And once you have the test, we can invert it to get a confidence interval, right? Because in many cases, we don't care about the p-value itself. We care about the confidence interval. And here, you can just do the direct inversion. So for example, here, you can try every value of beta 1, or you can try a grid of value of beta 1. And then every time you subtract x1 beta 1 from y, then that will give you a null case. And you calculate this p-value, and you collect all beta 1 such that this p-value is above alpha. And this will be a valid confidence interval in finite samples. And the rest of the computation is, yeah, it's just illustrating how to do this. So it turns out that in this case, we can write down the confidence bound simply as a minimum of things. So it's very easy to compute, where the numerator has to do with those linear combination of y, and the denominator is the signal to noise ratio. Okay. Then we have done a lot of simulations. And again, as I mentioned at the beginning, we're not proposing some methods superior to others. So it turns out those permutation tests are pretty robust, even if there's no theory under very general assumptions, but they're robust. So perhaps if we were to advertise one methods, we should still advertise those existing permutation tests. But here, this is just to show you what happens with some types of design matrix and some types of errors. So the first example is we generate Gaussian X, but then we fix it to make this a fixed design linear regression, and we generate Gaussian error. And then here we set the sample size to be 1,000 and P to be like 40, 33, and 25. So that the ratio is like 25, 30, and 40. And then we generate many copies of X. And for each copy of X, we generate multiple copies of epsilon. So that for each X, we can get this type 1 error. And then across different realizations, we can get this box plot to show the variation of the type 1 error. And here, we consider 3 versions of our test with strong, weak, and random row ordering. By ordering, I mean, so here strong means we apply genetic algorithm with many, many samples. And by weak, we just mean that we apply genetic algorithm with a few samples. And the random ordering is just take a random permutation. And then here, as a comparison, we also include the Friedman-Lane test, which is the residual permutation test, and also the test based on the least absolute deviation regression. But here, the disclaimer is that we're just using the asymptotic-based test for LAD. We're not using Bootstrap because Bootstrap is more robust. But you can see even with 1,000 samples and just like 1 or 2 dozens of variables, the LAD would have an inflated type 1 error. So that means that the asymptotic doesn't really kick in this case. But for all the other tests, they're pretty much retaining the type 1 error. And this is about power. So here, in order to study power, we need to give beta a particular value. And here, I just tune the beta 1 such that the t-test has 20% of power as a benchmark. And then we compute the ratio between our test and the test to be compared. So you can see that when N over P is like 25, which is slightly larger than 20, our test does have a lower power. But as things goes to 40, and as the signal strength goes larger, then our test is reasonable. I wouldn't say it's very powerful, but it's reasonable. And the next case is Cauchy X plus Cauchy error. Everything else is the same. And in this case, we know that t-test is not good, but it's not good in the conservative way. So actually, I have spent a lot of time trying to get a case where t-test violates the type 1 error, but I can never get it. Maybe you can get like 0.5% of violation, but I can never get that. So if anyone has some experience with t-test, then please let me know. And for LAD, on average, will give you the right type 1 error, but it has large fluctuation. And for the power, you can see our test is marginally more powerful than the t-test, but compared to the Friedman-Lane test and LAD, is still less powerful. So in the last 2 minutes, I'm gonna make just a few quick comments. The first one is this N over P bigger than 1 over alpha essential? So at first glance, it might seem to be essential because like it basically says that for every covariate, you have at least 1 over alpha samples. But it turns out it's not. I mean, if this were to be essential, that means if we want to test this hypothesis at level 0.005, which was suggested recently by ASA, then we would need N over P to be greater than 199. And that's almost never the case. But turns out we just need N over P to be bigger than 8 for alpha equal to 0.05 and 14 for 0.005. And I'm not going to delve into this. This is even crazier. And we're not sure if this has high power. So the trade-off between the type 1 error and type 2 errors is very unclear. And this is an ongoing project with Peter, but I put a question mark there because I really don't know if we're going to pursue that. And here are some open questions. Like first, can we do some approximate CPD? So here we just use the exact CPD. And we want that invariance to be exact. But what if we allow us to be approximately satisfying that invariant to the cyclic permutation group? Then maybe we can relax the N over P ratio condition a lot. And also, this test doesn't work for heteroscedastic linear models. And how to deal with that, or how to deal with the structure error distribution, that's another question. And finally, it seems like this test is hinging on the linear model. And it's unclear whether we can generalize that to generalized linear model or other nonlinear models. So just wrap up. In this talk, we proposed the cyclic permutation test, which is valid in finite samples for arbitrary fixed design matrix and arbitrary exchangeable errors. And it has exact type 1 error if 1 over alpha is an integer. And it's non-randomized if the ratio between the sample size and the number of nuisance parameter is greater than 1 over alpha. And through simulation, we show it has reasonable power if that ratio is much bigger than 1 over alpha. So the main message I want to convey here is how to partial nuisance parameters while maintaining group invariance. Because I think nuisance parameters and group invariance are two big topics in statistics. And when they meet each other, can we really deal with them? That's the general question I want to ask, instead of just proposing a method. And lastly, I want to encourage you to check out our literature review, because many of you are much more knowledgeable about the history than me, and I really want some help on whether I'm missing some really, really important work. And with that, I'd like to thank you all for your attention, and happy birthday, Peter.
To learn the long history. So how many different tests have been proposed in that long list? 20, 30, 50?
I think more than that.
So suppose you to take a random data set from UC Irvine.
Yeah.
What do you think the conclusion will be different based on these different tests?
I think for those permutation tests, this is my general observation. For this permutation test, like Friedman lane, it's going to be like the best. It's very robust in almost every data set. And I couldn't find a case that this is not good. But then for some other tests.
No, my question was really like how many of them going to make a different decision?
Right, right. Most of them are similar, I would say. Yeah.
So from practitioner point of view, how going to help them choose? That's why people do t-tests, right? Is that, do we want to need more tests?
Yeah, that's a great question. I think maybe we don't, right? So we know that t-test itself is not that robust, but permutation t-test is very robust. So maybe that's the only thing we need. Yeah. So here, the whole point is just to say like, yeah, is this what I'm making? So like, I don't know. I don't think this test is going to be useful, but it's really about the idea about how to combine nuisance parameters with group invariants.
Thanks for the presentation. My question is really about the clarification. I may have missed some part of your procedure, but you showed that type 1 error is guaranteed when you set delta to be 0. But do you always optimize to find that delta, or like if you happened like under the like say null model, and you happened to optimize for that delta, and you use the non-zero delta, is type 1 error still guaranteed?
Yes, yes. So here delta it's just a coefficient for the signal to noise ratio. So here delta will give you a difference between the first one and the rest of them after multiplying by beta 1 star. So if beta 1 star is actually 0, then this delta doesn't matter because they're still the same. So I would say this delta times beta 1 star is the signal. It's the signal strength. Okay. Yeah. So this will still maintain the type 1 error because as long as you have those constructions, then you will be guaranteed to have the.
Okay. Yeah. Now I see it. Thank you.
Thank you.
I have a question on the computational aspect. If M is small, you can just do boot false over all possible permutations, right?
Yeah.
So what if, can you do like a divide and conquer? If M is large, split it into 2 subparts, you know, do permutations on one and on the other, and understand which combinations will give you a large delta without, you know?
Yeah, but here you see that's a great question. But here, this is a permutation on N samples. So if N is small, like 20, then you can do that. But typically the sample size is not that small. So you should still apply some algorithm. It doesn't have to be genetic algorithm. So for example, you can imagine that this is a combinatorial optimization problem, and you can think about some convex relaxation. We actually discussed that in the paper, and maybe you can use that to find a good approximation very quickly. But I think the exhaustive search is not realistic in typical problems.
All right. I think we can take remaining questions offline. Before we, yes, Peter, you may.
First of all, I'd like to make it clear that although I asked some questions which were relevant, this very clever idea is really essentially Lihua's. The other thing is that there is, this project that might take place, would it be looking at other subgroups in the cyclic group, right? Where you could maybe get better control of the type 1 error, and possibly larger power. However, I think the real question is not so much with this particular test, but the interesting question is, when can you use subgroups of the permutation group in a useful way to enable distribution-free testing? Anyway.
Thanks, Peter.
Peter, so just one quick announcement before you disperse for lunch. Ashley, the Simon staff is waiting outside to take a group picture. So we'll just do just outside when everybody comes out, right, Katrina, that way in the back where the coffee was. And then we come back at 1:40 for the last session. Let's thank both our speakers again.